Okay. So what you're going to see here is everything that we've got to do. That's it. Normally you get 2 weeks and it's due on a Sunday, but this is the last one. So the last one is kind of hodgepodge. What I mean by that is that this one will not be due until Sunday, the 6th of December. But you got to remember we've got Thanksgiving in there and a whole load of other stuff. So you're going to be, if you're doing your job correctly, you're going to be really busy. So my strong advice to you here is don't wait until Sunday, December the 6th to do all this homework, because you will go grey and lose a lot of hair really quickly. Right? And the Monday after that's going to be a test. So you want to make sure that you've got that. So you can see that there's 5 sections, so it won't be much of a surprise to know that your last test will have 5 questions in it, 1 from each of those 5 sections. At least that's my plan. And so the guy...
This is this upcoming Monday or the Monday after Thanksgiving?
It'll be December the 7th.
Okay.
So December the 6th is when all 5 homeworks are going to be due. And Monday, December the 7th, a day that will live in infamy, because I was born on December the 7th. It's my birthday, which is not a fun way to spend your birthday giving exams, but I think that's karma.
It's the 3rd Sunday from now, I think, right?
I think so, yes. Well, yeah, whatever. Is it like 2 weeks and so many days? Right. 2 weeks and 5 days.
Because like we've got next Sunday and then the Sunday after, and then the one after that is when it's due.
Sounds right. Yes, exactly. So those are the guys. As soon as we finish something, I would do as much as you can. Just keep up to date. It's just the safest thing to do. And you shouldn't be too... I have... Okay, I was just looking at someone's comments there. Let's get started. Right, I went and upgraded, if that's the right word, to the new Zoom. So I'm kind of hesitant that something's going to fall apart. That's Green's theorem. Let's hide it and talk about a simply connected curve. We are going to do line integrals on a connected curve, right? A simply connected curve. So I want you to imagine that is a curve. It's 2D space. This is called the positive orientation. One way of looking at positive orientation is that you're going round the shape, right, the region, right, in an anti-clockwise direction. If you think about this simply connected curve, simply closed curve, it contains a region inside it. If you walk round the shape, and the area of that shape is always to the left of you, then you're going round in a positive orientation. Why is that important? Well, if you go round in a negative orientation, your answer will be negative what it should be. It's a bit like the integral from 1 to 2 and the integral from 2 to 1, right? If you do it one way, you get a plus, and the other way, you'll get the negative. So far, so good. Now, we're going to call this guy C. And the region inside, I'm going to call it D. And simply connected, right? I think of this as just meaning one blob. You are not allowed to do curves that cross over. So can you imagine this curve? Well, it doesn't really matter what direction I'm going, I guess, this one. Because in this case, I guess basically, don't you get 3 regions? So simple, nothing crosses over, positive orientation, and the whole thing's connected, right? So you can't have a curve. Nobody would have a curve like this, I doubt. They're not connected, agreed? Now, if you wanted to do this, wouldn't you actually do 2 separate line curves? So it's not like you couldn't. I guess if you wanted to do this, you'd have to orientate it a little bit differently and split it into 3 distinct ones. So far, so good. Now, suppose you wanted to find a closed, simply connected curve. You'd use that notation. Do you see that the integral symbol has a little circle around it? That's basically just means that we are looking at C as a simply connected curve, right? Suppose you are going to do a function, a line curve, I should say, that looks like this. We've seen line curves like that before, right? Now, if I call F this guy, if F is conservative, is a conservative field, what do you know about this answer?
We can use
what's a line curve equal to? If it's a conservative field and you start and finish at the same point?
0.
Which is what happens, 0. So you know you're not going to get many questions where the field, right, the vector field, is going to be conservative. Because if it is, you're just going to say equals 0 and move on. So we're going to be looking at calculating line curves, for the most part, when they are not conservative. And we are going to look at a subgroup. It's going to only be looped ones, right? Closed loops like this. So we're not going to do here and swiggle up to here, because that's what the parametric stuff that we did 2 sections back deals with, right? You know, where you start at A and you finish at B, and it's not conservative. You just do the, you know, parametric version, right? X is a function of t, y is a function of t, and you turn everything into t. It's that technique. So that ain't happening. And it's not going to be a curve to another curve and a conservative one, and because we dealt with that as well. Isn't that the one where you use the potential function to get the answer? So this one is going to be nice closed loop. So how do you do it? Well, here is the remarkable thing about it. Green's theorem says that if you have your function, your line integral like this, it's done on a closed loop, C, simply closed loop, then it is equal to this double integral. Now, the double integral is over the region D, and D is that one that's described by the closed loop. So can you imagine if I was doing this fella here? Then this integral, well, I'll have to put it over here, would be equal to the double integral over the region D of the partial derivative of Q with respect to X, take away the partial derivative of P with respect to Y, dA. And what's dA? dA will probably be dx dy, or sometimes dr d theta, right? And won't you probably use this version for dA and convert them into polar as well, when the region that you've got looks something like this? Can you imagine C was a circle? Could you imagine C was half a circle? Do you notice that in this case, the region D would be a circle, and here the region D would be that guy. And you would use the dx dy situation. So I guess I'll put this down here. Okay. That's what you use for dA. And you would use dx dy when your shape is rectangles. Right? Can you imagine that your closed loop's just going around a rectangle of some kind? Or maybe a triangle? Or where your curve is made up by the intersection of two other curves. Right? And in those situations, you're probably going to use the dx dy version of dA. So essentially what the Green's theorem says is that you can convert a line integral of a closed loop into a double integral, which was, God in Himmel, when did we do double integrals? Week 2? Something like that, way back in the day. And so remember all those things about how you find double integrals that we haven't done for absolutely ages? They're going to come back, right? So we're going to have to remember how to do, the limits of integration, not just with numbers, but with polar and with whatever the situation is. Right, so that's kind of the big picture. We are going to be looking for a line integral over a simple closed loop of guys that look like this. And according to Green's theorem, you can get that guy.
Can you show us that sheet with Green's theorem written down on it real quick?
There we go.
Thank you.
Okay. Well, I think like many things in maths, isn't it a little bit easier when you actually get to see it, right? So here's my first one. Let's do this fella. Y to the x dx plus 2e to the x dy. And C is 0, 0, 3, 0, 3, 2, and 0, 2. So we're going to find this line integral, and the closed loop is basically a rectangle. I think I should probably draw it. Let's see what it looks like. 0, 0 to 3, 0, 3, 0 to 3, 2, 3, 2 to 0, 2, and 2, 0 back again. So there's C, and there's D. We comfortable with that guy? Right, now, according to Green's theorem then, this fella don't mind, I'm just going to put you on mute. I'm getting some kind of background stuff going on. So we got this guy, and he is going to be the double integral, Priscilla, dq dx, take away dp, dy, dA, right? And we'll convert him in a second. Oh, by the way, if it is a conservative field, aren't these two things equal to each other? Remember the test for conservative? dp by dy equals dq by dx. And if they are equal to each other, do you see this just becomes the double integral of 0? Which is, you know, the answer, 0. Okay, so let's see what we get. I'm doing a double integral of this region D. If you do, call him P, call him Q. dq by dx gets you this fella. Take away dp by dy. Well, if you differentiate this fella, I believe you get e to the x. So far, so good. Right, now, based on this picture, do you think I'm going to go the dx dy route, or do you think I'm going to go the rdr d theta route? Am I going to go Cartesian or polar? Do you agree it's Cartesian? Now, if I'm going to do Cartesian, I can do dx dy, dy dx. In this case, it doesn't matter, does it? Because it's a rectangle. So for no other reason except alphabetical, I'm going to do that. That means that my limits of integration are going to go from x equals 0 to 3 and from y equals 0 to 2. And so that this fella becomes integral from 0 to 2, the integral from 0 to 3 of e to the x dx dy. Is this one separable? So I'm going to do 0 to 2, 1 dy, and 0 to 3, e to the x dx. And can I just go dot, 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 dot? Right, you could finish that, right? What's that, 2, and that's e to the 3. You could do it in your head almost. Now you might think, well, that's nice, you know, a guy called Green theorem. You take a line integral and you turn it into that. Imagine we were doing the parametric version of this, right? If I wanted to do it the parametric way, wouldn't I have to do 4 separate C's? Wouldn't I have to do that guy, then this guy, then this guy, and then this guy? Wouldn't I have to do 4 separate integrals and turn everything into parametric equations of 4 lines? And then each one of them you would use here, and it would take you 4 times as long, right? So Green's theorem is very helpful when you have got a closed loop. So far, so good. Right. Try another one. Suppose I do the line integral, closed loop, of what one? Let's do x squared y dx plus y squared x dy. It's got a little bit of symmetry to it. And let's see, be 0, 0 to 1, 0 to 1, 2 to 0, 0. I should have planned that, I should have. But what does that guy look like? To me, it's a very visual thing, at least that's the way my brain works. You start there, and you go to here. And then from here, you go to here. And then you go back here. Would you agree that's positive orientation? would you agree that the region D is actually a triangle? Oh, just decided to make a little change. Right, so this guy on this triangle, there's D. Well, according to Green's theorem, it's a double integral over D of this fella, take away this fella, dA. I think the reason I changed that, I was really worried that I might have ended up with a conservative field by accident and the answer would have turned into a 0. So at least now I'm pretty sure that I've screwed that up. We will call this guy P, we'll call this guy Q. So if you differentiate this with X, you get 2y squared. And if you differentiate this guy with Y, you get take away 3x squared. Okay, that's cool. Since this region is going to be a triangle, I'm going to do dy dx. And since my picture is pretty messy, I'm going to draw another version of it. I'm going to draw another version of it over here. If you want to describe this region, don't we take a random vertical slice and we're going to say x goes from 0 to 1. And won't y, well, don't I need to know the equation of this line? You agree? Actually, you should be able to do it in your head. What is the equation of this sloping line?
2x.
Okay, so won't y go from 0, the bottom, to here, which is 2x? Do you see how I've created the region D, the limits of integration that would create that triangle? If it's going to be a triangle, because that's a very common shape, won't you do x from here to here and y depending on the equation of the straight line, right? That kind of thing.
So because of the direction that the arrows are going, would it be from 2x to 0 instead?
Ooh. Yes. And I wouldn't have noticed that until I got the answer. And I'm going to say +7, and then it says it should be -7. But I'm going to say -7, it should be plus, because I was too busy playing about with it. To be positive orientation, aren't you going to go from 1 to there, right? Okay, so we are looking at a y value that goes from 2x to 0, and an x that goes, I believe, from 0 to 1. This particular question, I don't think can be tidied up, so here goes. It's going to be from 0 to 1. That guy's 2/3 y cubed, take away 3x squared y, evaluated at y equals 2x to y equals 0 dx. Okay, can I dot that? It's just messy. It doesn't take a great deal of time. Are we cool on that? Right. Oh, it'll be some horrible polynomial in x cubes and so on and whatever. Right. Try another one. What have we done? We've done a rectangle, I've done a triangle. So I should do somewhere a circle or bits of a circle, right? And something to do with a function, you know, between the two functions or one function. So I should do that next. So how about the integral of 3y plus 2e to the square root of x dx. By the way, this is a version of 3. Plus 4x plus 2 cosine y squared dy. And the c is the boundary between these two curves. So it's between y equals x squared and x equals y squared. Right. So over here, if I draw y equals x squared, it looks like this. If you rearrange this, don't you get x equals the square root of y? It's just basically a rearrangement of that guy. Are you comfortable about these two generating this? Now, when I'm looking at the shape, won't I come along this way and go that way? So the region D that they are after is basically that region, isn't it? Looks a bit like a fish or a cigar. So it's going to be the double integral over the region D of the partial derivative of this fella, take away the partial derivative of that fella, dA. Don't I need to know that that's 0? And I think it's pretty obvious that that's 1. So x is going to go from 0 to 1. In this particular case, if you take a typical start and finish guy, we've got this fella and this fella. So what we're looking at y equals square root of x. That's what I meant to say. So y equals x square root of x, y equals x squared. This horrible mess is p. This equally horrible mess is q. Let's hope the derivatives come out nice. If you differentiate this fella with respect to x, doesn't this mess here doesn't matter? The answer is just 4. And if you take this horrible mess, but you differentiate it with respect to y, doesn't this just go away and you're left with 3? Oh, come on. That is so elegant, isn't it? Again, this one here would be a dy dx world, right? So I'm going to do the integral from 0 to 1 from y equals the square root of x to y equals x squared of 1. Can I just dot that guy? Can you see that? Maybe this is slightly artificial, but can you see how simple a closed loop line integral can be using Green's theorem? Because double integrals tend to work better, don't they? They tend to separate, or they tend to, at least here, generate really nice results. If I had to do the same question parametrically, and it wasn't a conservative field, because if it was, the answer is always 0, wouldn't it be an atrociously big, horrible, long question? You can even try to imagine it would be scary. Have I sold you on Green's theorem as a good way of getting line integrals? Then my job is done. So now I need to find an example of Green's theorem where the closed loop is something circular. So something, didn't take long, question 4. Or at least like 4. We're going to do a 2y cubed dx. Okay, I'll trust them. 2x cubed dy. And c is the circle. X squared plus y squared equals 16. Now, since we're talking about this circle here, right? Wouldn't that come out, if we think about that, wouldn't the dA that I'm about to do, wouldn't it come out really nicely in polar form? So it's going to be the double integral of the region D, which is basically that guy, of this fella, dA. Now, your P and your Q. If you differentiate this with respect to x, you get 6x squared, and this you get take away 6y squared. I'm going to do r, dr, d theta, and since it's a complete circle, can't we do r equals 0 to r equals 4, and theta equals 0 to theta equals 2 pi? Are we comfortable with that? I've still to turn 6x squared, take away 6y squared into r's and thetas, so maybe I should do it over here. It seems to me reasonable that pulling out 6 might help. Can you remember what x and y are in polar form?
R cosine theta, R sine theta.
Agreed? So wouldn't this become basically r squared cos squared theta, take away r squared sine squared theta, which means I can now pull out an r squared and get that. And nowhere in math does anything disappear forever. No, that is not 1. Cos squared plus sine squared is 1. But it is something. It's a trig identity. It's a double angle.
Isn't it sine of 2 theta?
Go the other one.
Cosine 2 theta.
Yeah. Why is that important? I can integrate the cosine of 2 theta without too much trouble. I'm going to have a really hard time trying to integrate sine squared or cos squared, agreed? So this fella now becomes the integral from theta to 2 pi of 0 to 4 of 6 r squared cosine 2 theta times an r, a dr, and a d theta. Are we comfortable? Right. Now I'm going to do kind of 2 things at once, but hopefully it's not too bad. Are you comfortable with the fact that I can split them into 2 separates, right? The integral separable. The cosine 2 theta from 0 to 2 pi and 6r times another one, 6r cubed from what, 0 to 4. And dot, 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 dot. Are we good? Right. Let's keep that question for a minute. And we'll keep all of this the same. So that means 6r cubed is going to be the same, cosine 2 theta is going to be the same. But I'm going to do one major change. Let's suppose it's not the entire circle. Let's suppose you only do the half, the top half. Won't the only change be to the thetas? And what will the thetas be in this picture?
0 to pi.
Be careful.
Negative pi over 2 to pi over 2.
Are you comfortable about why that needed to be done in that particular order? You're going from here and you're curving up to there. Are we good? Now, if you ever do one of these and the answer's 42 and it says it's wrong, well, you try negative 42. And if it's right, it just means that you got your positive orientation back to front. Because some of these shapes, as I've already done at the start here, if you're not very careful, you get the orientation slightly wrong. Right. So it might be pi upon, you might have to switch places, right? I think this is going pretty smoothly. That's the vibe I'm getting. It's not the worst looking formula in the world, right? And it does double integrals, which we're hopefully familiar and comfortable with. Right. Any questions where I just randomly pick another example? Okay. For a few seconds then, will you all say hi? We'll take attendance right now. Okay, here goes. Okay, and I'm going to pick C. Who shall I pick C? Let's do a triangle floating in space. Not all triangles have to go through the origin, right? It's going to be this fella, that guy, DA, and this fella's P, and this guy is Q. And I deliberately chose the ugliest looking function in the world. When you differentiate it with respect to X, you get 0. Agreed? And this guy with respect to Y, you get that guy. Now, since my region is a triangle, would you agree we're just going to go dy dx? And we're going to do y equals to y equals and x equals to x equals. Well, in this case, this triangle goes from x equals 0 to 2. And y is going to go from 1 right, to there. And won't there be whatever the sloping line is? What is the equation of this fella? You agree with the slopes too? No, it's not.
I think it's just x plus 1.
I'm just checking my slope. This is 2 by 1, so it's actually a half x plus 1. If you do a quick check, the slope's a half. I kind of screwed up, but I caught it in time. Right. So it's going to be y equals 1 to 1/2 x. So what does that end up becoming? Well, this is separable then. Well, not separable. I take that back. So x is going to go from 0 to 2, and this guy is going to be negative x squared y, evaluated at 1.5 x.
You forgot to add the plus 1.
Walk up. Okay, actually, I'm looking at my watch. Can we just dot that? Would you agree it's just some polynomial? So Green's theorem's got a little niche market, isn't it? It's going to allow us to find a line integral of a simple closed loop. And it is very helpful for rectangles, triangles, and bits of circles. But you can also use it for areas between two curves as well. I think that's a nice place to finish, isn't it? So to remind you, if you haven't already, I don't know, you may have come in late. If you didn't get your report, that you want to send it to an email to me so that I can send you your grade back individually. I've done everything I can as far as my spreadsheet goes, but somehow between leaving here and getting to you, some of you just don't get it. Any questions, or are we good for today? Okay, I'll see you again tomorrow. Have a nice day.
Thank you.
You're welcome. Okay, Ashton or Chris, if you have a question, I'm here. Otherwise, I'm just going to close off.
Did you get my email with the work shown?
Yes, I did, Chris.
Okay.
Okay, so we're good to go then.
Okay.
Right, bye-bye.